Hi, I'm Ru. I will be presenting our work, an empirical study on program failures of deep learning jobs. This is a joint work with Wencong from Alibaba, Hongyu from Newcastle, and Yu Haoxiang Mao from Microsoft. To help data scientists train and test their deep learning models, enterprises build deep learning platforms, allow developers submit and execute their deep learning programs. Philly is a similar deep learning platform internally used in Microsoft, built with widely used open source technologies and typical computing hardware. Here is an overview of the job lifecycle. Developers first upload their code scripts and data, then specify the job configuration, such as the number of designed GPUs, main Python code file. Once a job is chosen by scheduler, Felix instantiates Docker containers to execute the launching shell script and later run the main Python code file. The job may fail if a Python exception or shell error code is thrown. Every day, thousands of deep learning jobs are submitted to Philly. However, we found that a noticeable percentage of these jobs throw a runtime exception due to code or script defects and failed to complete. For example, this job had been running for 40 hours on 4 GPUs for training, but then triggered an exception due to a wrong path configuration of evaluation fail. Therefore, reducing job failures is very important for saving precious resources, improving developer productivity, and creating business values. We propose one of the first empirical studies on program failures of deep learning jobs. To investigate failure classification, we chose 4,960 failed jobs caused by developers' code script defects. We called this set the full sample set. To further understand the root cause and fixes, we randomly selected 400 out of the total failed jobs and performed a detailed analysis on them. We call this set the small sample set. Its classification overview. The figure illustrates the failure distribution across the four dimensions. 1. Execution environment, such as the file or directory used in program cannot be found. 2. Deep learning specific, including GPU out of memory, tensor mismatch, and so on. 3. General code error, which means the common errors we met while using Python programming, including illegal argument, type mismatch, and so on. 4. Data. It consists of corrupt data and unexpected encoding. Deep learning specific failures are divided into 5 categories: GPU and CPU out of memory, framework API misuse, tensor mismatch, and lost none. Here is an example of GPU out of memory failure, the largest category in this dimension. The developer constructs a sequential model with a LSTM as the core layer. The input would be fed to the model in groups of data items called batches. If the batch size is too large or the model is too sophisticated due to the overlong LSTM layer, the job will consume much more GPU memory than the capacity and crash. The fix is to reduce the batch size, the max context length, or both of them, while keeping the model learning performance acceptable. Here is an example caused by framework evolution. The developer may have thought that the latest version of Keras would be compatible with TensorFlow 1.3. However, Keras upgrades its softmax implementation and requires TensorFlow 1.5 or higher. The fix is to downgrade Keras to a compatible version. Here summarize the findings. 13.5 of the total failures are deep learning specific. They are mainly caused by inappropriate model parameters, structures, and framework API misunderstanding. Developers need to choose the suitable model configuration and deeply understand the assumption made by framework library APIs. Based on our findings, we further suggest the following possible research topics. First, memory estimation for deep learning model, which could avoid the GPU out of memory crash during the program execution. Second, deep learning specific static code analysis, which could help reduce tensor mismatch or other failures. API evolution analysis, API misuse detection, and dependency analysis could also be useful. Execution environment related failures occur in the interaction with the platform rather than in the execution of code logic, accounting for nearly half of the total failures. Root cause is that job execution environment provided by a platform is rather different to that for local development. Here shows an example of pass not found failure. The developer first used training file to train the model, then evaluated the model with the evaluation file, but she forgets to replace the hard-coded local file passes with the real ones on the distributed storage before job submission. The fix has two parts. First, all the passes are parameterized instead of hard-coded strings and are read from the configuration file. Second, passes used in no matter which stages, such as the eval file variable, are validated as early as possible. Execution environment-related failures are mostly due to unawareness of the environmental differences between local and platform. Developers need to fully understand the environmental gaps and write environment-adaptive code and verify passes permissions as early as possible. Here are some possible research work we suggest. Platform can provide a local simulator integrated with IDE. It could help avoid the developers take the platform as the test bed to reduce the execution environment related errors. Platform support of lightweight job pre-run and automatic code adaptation for platform could be also useful. We have conducted one of the first empirical studies on failures of production deep learning programs, including failure classification, root cause, bug fix, solution analysis, and developer interviews. Based on our study, we suggest possible research topics and tool support. Due to the time limitation, I can only present part of our work. Please read our paper to know more details about our work. Thank you, everyone.